Hi everyone, I'm Sanju Shashi, and today I'm going to present PRAC, Round Efficient Three-Party MPC for Dynamic Data Structures, which is joint work with Aditya and Ian Goldberg. Alright, so MPC protocols have been studied for several decades, and we're now at a point where computations in the circuit model can be efficiently realized by MPC. The main bottleneck for MPC solutions are typically communication-oriented, so the rounds of computation, the rounds of communication, and the bandwidth overheads involved in these communication rounds. While circuit computations are efficiently realized in MPC, computations in the RAM model, in fact, pose a challenge. And so in MPC, RAM itself is typically realized via distributed oblivious RAM protocols, or DORAM protocols. And broadly speaking, there are two such DORAM types of protocols. There's communication-efficient DORAMs, like DORAM and FlowRAM, and computation-efficient DORAMs like Raman and 3PCORAM. So in this work, we present PRAC, Private Random Access Computations, a three-party MPC framework in the semi-honest setting for random access data structures. So PRAC extends the state-of-the-art communication-efficient DORAM with implementation improvements and extensions based on distributed point functions. So we take advantage of some interesting properties of DORAM, the state-of-the-art communication-efficient DORAM, that make it well-suited to support RAM data structures. And in particular, our work presents three different protocols that are exemplar of data structures with varying degrees of what we call data dynamicity. So in particular, we present an oblivious binary search that is static in nature. That's to say it operates over assorted secret shares of an array of data on an oblivious heap that allows for arbitrary additions but deletions for only the minimum item, so we call this restrictively dynamic. And also the first oblivious AVL tree protocol in the distributed trust setting, which allows parties to insert and delete and look up in this AVL tree without any party realizing the items or the shape of the tree that's involved. Alright, so first let me provide some background. So at a high level, computation-efficient DORAMs are based on either tree-based or square root-based ORAMs from the traditional client-server model. And so such schemes typically have sublinear computation, as you can see there in green, but they incur more bandwidth overheads than the communication-efficient DORAM counterparts. Now, the other crucial aspect that's relevant for us is that the logical RAM for n items in such schemes is in fact scrambled across a larger physical location, in particular m prime, which is strictly greater than the actual number of locations. Now, on the other hand, DORAM, being a communication-efficient DORAM, like other communication-efficient DORAMs, it incurs linear computation, as you can see there, but the advantage is it has bandwidth overheads that's logarithmic, and so better off than the computation-efficient DORAM. Now, the crucial parts that's relevant for us is that items in DORAM, it turns out, are laid out exactly as is in the physical memory as it is in the logical RAM. And moreover, it turns out the DORAM protocol kind of allows you to access subsets of this RAM essentially for free without paying any extra overheads, which is not true of the other world. So given that, the core techniques or intuitions that underlie PRAC's efficient data structures are you can gain efficiency for data structure protocols by explicitly revealing information that would have been inherently leaked by the algorithm. And we'll see some examples of that shortly. And we can do this by exploiting this memory layout property of DORAM and its ability to allow you to operate over subsets of the RAM trivially. And furthermore, it turns out we can make this efficient in terms of the bandwidth overheads by using DPF extensions, namely incremental and wide DPFs. Alright, so to give an idea of how this works, I'll describe how the oblivious binary search works at a high level. So let me start with the prior approach for binary search in the setting, which is by FlowRAM, and it uses log n DPFs to search over n items. And so the high level idea is with each distributed point function, one selects the current pointer of the binary search from this array, perform a comparison with that item, and then update the pointer for the next part of your binary search such that you continue this log n times. Now this protocol is clearly an overkill as it's essentially hiding each binary search pointer across these n items. But in fact, we all know a binary search access pattern has a very obvious access pattern that's induced by this binary search protocol. And so the idea is that in fact, if you leak this particular access pattern, you're leaking no more information other than the fact that a binary search is being performed across this array. And that's exactly what we do with our binary search protocol. And moreover, it turns out this particular access pattern structure is in fact the exact same one that's induced by what is called an incremental distributed point function. So it turns out you can do all of this with just simply one distributed point function instead of logarithmically many of them. And this saves you logarithmic overhead in terms of the bandwidth as well as logarithmic computational overheads as well. And so to quickly analytically compare our work with other approaches based for oblivious binary search, FlowRAM presents an oblivious binary search protocol with log square n, bandwidth and rounds, and n log n computation. So this arises from log n DPFs. That's where you end up with these analytics. And Raman and 3PC ORAM, the computation-efficient DORAM schemes, have sublinear asymptotic, as you can kind of see there, but they pay off more in terms of bandwidth and rounds. And PRAC, in the meanwhile, has the lowest bandwidth and round complexity, just logarithmic and n directly, but they have a higher computation, in particular they're linear. But nonetheless, as we'll see next, in concrete performance numbers, our linear computation overheads are still much better off than Raman and 3PC ORAM, as they can't take advantage of these optimizations we pointed out for our protocols. So for the experimental evaluations, we use a standard setup where each party has 100 Mbps bandwidth and 30 millisecond latency each way. And PRAC and FLORAM, in fact, have actual implementations of an oblivious binary search protocol, so we run them in its entirety and present the numbers here on this graph. The computation-efficient DORAM schemes, in fact, do not have a binary search protocol, so we estimate their costs. And I'll speak more about that shortly. But in comparison with FLORAM and 3PC ORAM, as you can see here, PRAC presents about 27 times improvements in the walk-up time, which is shown in seconds here on the y-axis. And note that this is a log-log plot, so a small gap is a large gap in practice. Now in comparison with Raman, our protocol presents about 61 times improvements, and also we note that this performance benefits I'm going to claim here are in fact pretty conservative because, as I said, these are estimates, but our estimates are only accounting for the DORAM axis, the cost for initializing and pre-processing a DORAM of that particular size, as well as the cost of performing each individual DORAM axis, but not the other costs involved with the other MPC operations required to perform a binary search protocol itself. Right, and finally one last thing I'll mention here is that you can see these dashed lines for PRAC, which actually corresponds to just the online cost of running our protocol, which it turns out, because PRAC is based upon DORAM, which admits an offline-online phase, wherein you just perform pre-computation in the offline phase of constructing the distributed point functions, you can gain speedups in the online phase by just utilizing them. And this gives you about another 4x factor of improvements in just the online cost phase. In terms of bandwidth, at the same 2 to the power 26 point, PRAC presents more than 3 orders of magnitude improvements over 3PC ORAM and FLORAM, and more than 3.6 times improvements over RAM. And again, in the offline-online split, you can get another order of magnitude improvements over the improvements that I just mentioned. Now for heaps, we present a basic and optimized variant of heap insert and extract min protocols in the paper, but here I'm just going to speak a bit about our heap insert protocol, but please refer to the paper for more details on how the extract min protocols work. So a high-level overview is that, let's say we want to insert a new item into this particular heap, and let's say this item is 13. So we create a new empty node at the next available location within this DORAM, and then this essentially fixes the path to the root from this newly inserted node, but this is a newly inserted empty node. And now, at this point in the basic version, you simply perform logging comparisons along this path to find out where this location would end up, and you leave and replace it there. So that results in a log and round complexity protocol. And so, in our optimized version, we use this by using our binary search protocol to figure out the final location where this object would end at. And this gives you a log n complexity in rounds because you're performing a binary search over this log n path. And finally, once you do this binary search protocol, you perform an oblivious trickle-down operation with the result of this binary search protocol, which effectively leaves an empty slot for where the final location of this inserted item would be. And you complete this insertion by just doing a heap insert with an oblivious tracking of this particular path. And I should point out again that we can do all of this only because the underlying DORAM allows you to access just a subset of this ORAM trivially. And so we're basically leaking the fact that you're applying this heap insert on this particular path. But once again, that's leaking no more information than the fact that a heap insert is being performed along this particular path, and that's perfectly fine. And so this results in a protocol with of log n bandwidth and of log n rounds because of the binary search over that log n size path, and a computation of log of n because your DPF is only operating over that particular path of log n size. I'll point out that Muslim and null actually present an oblivious priority queue protocol within the malicious secure model, with it has of log square n bandwidth and rounds and computation. And unfortunately, they do not have a publicly available implementation, so we do not have experimental results against this construction. But in the paper, we provide experimental results that compare our oblivious heaps with instantiations based on the other DORAMs, with which our results present qualitatively similar results, just like what we saw in our binary search. So I won't show that here in the interest of time. Finally, I'll speak a little bit about our oblivious AVL3 protocol, but I'm not going to go into the depth of the construction here. So consider this setting where you have truly dynamic data, which needs to perform insertions and deletions and lookups over. And the natural data structure, of course, is in fact binary search trees from algorithms courses. But binary search trees have this worst case cost that's linear in the number of items you're operating over. Moreover, when you're in an oblivious setting, you in fact have to necessarily incur this linear worst case cost because otherwise you end up revealing information about the structure of this tree. And so AVL trees are a classic solution from computer science algorithm courses towards alleviating this worst case problem of binary search trees. And so in our work, we present the first AVL tree construction for the distributed trust setting where no party learns the items deleted, inserted, or searched over, all with logarithmic asymptotic complexities in terms of bandwidth and rounds. And the key challenge that really underpins this work is how do you design oblivious circuits that in fact resolve the rotation processes involved in imbalances that arise in an AVL tree protocol. And so all of that is addressed in detail within the paper, so I encourage you to check the paper out if you're interested in those cases. And so to summarize, in this work we present PRAC, a generic framework for random access computations for three-party MPC. We have new rounded bandwidth efficient protocols for oblivious binary search, heaps, and AVL trees. And in the paper, we'll find more details on the algorithms for our data structure protocols, detailed experimental results, and even an evaluation for a distributed stream sampling application based on our heaps. So thank you. With that, I'm happy to take any questions you have.
Thank you, Sachin. Do you have any questions?
I see Marina.
Okay, Marina.
I wanted to ask about the heap protocol. When you said that it's okay to reveal the path, is that because the nodes are randomized?
No, it's kind of like saying, so let's put it this way, the tree is still secret shared, but we're basically kind of exploiting the fact that the way it's linearly laid out in memory corresponds to the underlying tree structure by the classical way. And so when you insert a new node, the fact that this is the last inserted node dictates that path, which is not controllable by anyone else, right? And so that's why it's okay to leak that particular path. I see other hands.
Yeah, there is this one. Go ahead.
Oh, sorry.
Yeah, I have a general question.
Yeah.
How would the framework scale for more than 3 parties?
So because it's based on DPS, it really, we are using it for mostly 2 parties. The 3-party comes into the fact that the underlying distributed ORM is a 3-party ORM. But we don't have currently any scaling mechanism for more parties at this point. We haven't considered that part of it at all.
Thank you.
Thanks for the talk. Maybe could you give us some intuition behind the AVL reconstruction? Like, how do you know how to balance and when to balance the data?
Right. So unfortunately, I don't have any slides on that part of it. But let me give you a very high level gist. Is that in the insertion case, it turns out if you look at the AVL tree protocols, it results at most at 1 rotation at the end of the tree, more or less. And so you can perform 1 rotation over the entire tree and get away with it. And we explain in the paper how this rotation works. It turns out you can complete an imbalance rotation with, let me say you can resolve an imbalance with exactly 2 rotations. And so we always perform 2 rotations, really, right? Sometimes some of them is a fake one, but sometimes it's a real one.
Okay, so sometimes that you rotate that actually you won't do anything.
Precisely.
Okay,
and sometimes you're basically not doing a rotation, but you pretend to be doing the operations involved.
Thanks.
Yeah, for sure.
Any other questions? Cool. Thanks, Gina.